This meeting is being recorded.
So recording to the cloud. And hi everyone, welcome to our machine learning barbecue meeting, reading group. And today we have Mohamed presenting segment anything model for medical imaging or foundational model. We'll see. Okay, go ahead, Mohamed.
Okay, thank you. So today we'll talk about the foundation model for medical images. Looks like a uh, recent breakthrough coming to the image segmentation in general. So last year, the Meta AI research people get their paper out for the segment anything, and uh, the purpose at that time that they wanted creating a foundation model that can generalize for any type of object, and actually didn't ask for the end user to get their labels in the, for get segmented their own data. I mean, in order to do that, they actually try to create a large data set, and these data set actually have like 1 billion masks, and from there actually they create their model. They make like three main components for that. They had like a task and a model and a data and the data engine in this case. And for each part of that, actually, they tried to generalize the idea that we can segment anything. So they expected a prompt come from the end user, and this is can be like a bounding box or point, or even a mask or text. And based on that, there is an input image, and there is a segmentation result internally for the model itself. They have multiple components. We will go over that in a second. And they actually have some algorithm or maybe strategy to create their large data set that used in the training here. So for the for the purpose for training here, they tried actually to make a simulated prompt generation in the beginning. So this actually used to propose some potential input, mimic this potential input. It can be like an object or bounding box or text, and they make this prompt associated with specific training image. So this is actually the part that they are using during the training stage of the SAM model. So SAM here is the abbreviation for the segment anything model. Again, they have like this beard ground truth masking, and trying actually to use all this in a supervised way to train that actually model. They had like a double loss function here, the dice and the focal loss, in order to capture the hard misclassified image part or region of interest. And internally, actually, they have that overview of the SAM model here. So the image coming in a certain dimension. I guess it's like 1024 by 1024, and it has to pass through an image encoder to get the image embedding. And meanwhile, there is the prompt by the end user when they are going over this image and trying to select a certain region by clicking a point, or by specify a bounding box rectangle or shape. So that actually part also get prompt encoder, and they actually both of this embedding data get fusion in the mask decoder part, and they generated like multiple output, like three output in this case, with confidence score, trying actually to get like multiple segmentation results each one of them can be different a little bit, and they take the average at some point of that, getting actually the final result. So here actually there is internally they don't discuss a lot about that, but basically the image encoder here used like a masked autoencoder. So this part maybe can help in getting a better performance, or also can be indirectly help in the ambiguity objects, where there is a part of the object is not actually complete. So when we try for that part, the masked autoencoder here actually trying to batching that input image and trying to actually to mask some of the batches, and in a supervised way it trained to actually predict that hidden part automatically, and then these go to like an image feature in the last of this stage. Uh, Again, why that's specifically masked autoencoder used for the image encoder here? This can be actually for the accuracy of the model, performance, or maybe for the ambiguity of the objects. There is a part of the mask here that can also be an input for specifying a specific region to segment, and for the points and box and text, each one of these actually encoded in a different way. So for the points, there is actually an embedding or decoding process, getting the position of the point where it is, and whether it is a foreign or background point. For the box, they actually also getting the positioning encoding here. So there is a part extract the top left and the bottom right points for that pointing box, and getting the actually encoding that part. Text, they depend on the clip model. So in the clip model, we have such actually two inputs in this case, like a text and an image feature, and there is a vector can actually associate between the parts of these actually two inputs. So finally, once all of these things come together, there is like a mask decoder in this case. So in the mask decoder, it used the cross attention in order to fuse between the image feature and the prompt feature, and started from there. There is a process like the using the upsampling to retrieve the original image again, and then go to the sigmoid activation function to get the pre-mask in the end. So this is
Is
actually
it,
the overview.
Mohammed?
Yeah.
So the lightweight mask decoder is a CNN, or do you know what is it? What architecture is that?
Which one? Sorry.
The lightweight mask decoder, is it a CNN?
It is actually a transformer. I guess they didn't get in details, but in general, some mentioned that it can be like having like mainly 4 layers, like the part that the MLB layer, there is a part that talking to image, and there is a self attention, and there is a cross attention also. So this is like mainly what it there. It is a vision actually a transformer.
A transformer. Okay, thanks.
Yeah, and there is a part after that part. There is a transposed convolution when we are trying for the upsampling. So this is coming a later stage, I guess. So so this is actually all this process depend on the pre-training in the beginning, and that pre-training started actually with a limited number of images that is labeled manually. And from there, actually, they start like using some public segmentation database or data sets to train their images and get the masks for them. The manual, actually, in the first stage, the manual annotation by annotators have been heavily here, and based on the result of the first stage, they get like maybe 10% of the whole data set they have in the end being ready at that point, like maybe more than 100,000 image and corresponding masks have been found at that first stage. Then they went to the second stage, which is a semi-automatic stage. In that stage, actually, they used the image from the first stage and their mask to train again the model, and there was like a part when the annotators come to just adjust or find the object that not correctly allocated in the image. And based also on this actually stage, they get another maybe 20% of the whole data set they create in the end. So the total of the both stages, the first and the semi-automatic here, was around 300,000 image and their masks. The masks maybe can be like more than 1 million here. Finally, they go to the fully automatic stage, and in that stage, they get their whole data set with around 11 million image and more than 1.1 billion masks created. So this is actually the data set they used for the training of the SAM model. Of course, each one of these have, as we said before, there was like a simulated prompt input to train the model on different actually type of prompt that the end user can, or maybe it can actually created by the end user. However, this the SAM model, even it is working good on the nature images, but it doesn't perform good on the medical images. And in this actually, in this paper, the authors actually try to make some evaluation for the SAM model on a, on a, on a liver tumor segmentation dataset, and they proposed like a metric here to see if changing the number of points or changing the resolution of the image can affect the accuracy of the segmentation or not. And they found actually, like in this image here, when there is an increase actually in the number of points, there is actually increase in the segmentation accuracy, which actually mean that we don't know specifically how many points we need to use to get the right segmentation from the SAM model. And this is actually one of maybe the downside of SAM model in the medical images. In the resolution part also, they found that increasing the resolution can end up actually in lowering or decreasing the segmentation accuracy. So again, this is another downside of the SAM model in the medical field. And using different vision transformer here, from basic one to large and heavy one or huge one. So the performance was actually better with the huge one, but this huge one is not actually practical to be used, especially when we are doing like that process in the browser or in a cloud based. So this is actually reflect again that some parts of the implementation here maybe need a requirement that is not maybe practical to be implemented in some cases. So I just give it a try here to see maybe what they have a demo, online demo. Just one of our slices here come to test with the segmentation, everything, and we can see it is just maybe hard for the model here to find these tiny details. I mean, and it only end up finding the foreground and background for that image. It's like a masking actually for everything without specific find like gray matter or white matter regions. Even when I tried to see just as a test, I put the label itself. So the label here is distinguished between the gray matter and white matter. This is not the input image, the neft wire, but this is the label, the result label. And I found there is a need here, like for many points, to extract the white matter. And we had actually to find also or to indicate the area that we want to subtract by these pink dots. This is another actually evidence, maybe Sam, uh, good for natural images, but not maybe suitable for the MRI or medical. However, since this SAM model started or released, there have been like maybe 16 or 17 variant of that model dealing with the medical images. Uh, all these actually models come maybe within 1 year since it is actually released in the middle or April of 2023. So till the end of that year, actually, we see like maybe more than 15 or 16 variation of that submodel that's trying to solve the problem of medical image segmentation and create a foundation model for that. One of these actually is the one that the Miss Sam that we will talk about today. And in the Miss Sam, they actually trying to make the same idea transferred to the medical images. So the motivation that they had in this case that most of in the medical image we have that task specific segmentation models. We don't have that foundation model, and even the SAM model looks like attractive and have this zero shot image segmentation capability. But this attractive feature of the SAM model, which actually is showing that we can use something similar in the medical field where we have that rare data and a lot of annotation labor needed actually in that domain. But this capability actually is actually limited, very limited, as we see from the previous results. So they come actually with this mid-SAM idea as a fine-tune from the SAM model itself. They didn't change a lot on on the original model here. They just come to try to train the same model, almost the same model on medical data. And they use actually double approach here together, full fine tuning and parameter efficient fine tuning. They tried like it is not clear exactly how they did that in the paper and where they did that, but they tried to find a balance point between the efficiency and the computational requirements. So two challenges when they are trying for the medical images they are trying to address here. One of them is actually there is like inherent variability inherent in the segmentation task. So when you are trying to segment a medical image, the clinician here may be interested in a part that another one may be interested in a larger part for the same objects, which you have to decide what you need to actually train the model on, and how actually that can produce the segmentation part that interests for the major of the clinician in this case. They have this actually uh, diversity in the requirement when they asking for the segmentation of the medical image. The other part here is the variability of in image modalities. So in order to find that foundation model, this universe model, some model, some modalities here can be 3D, other like MRI, CT, and other can be only 2D, like the pathology images, for example. So combine all these things together is also another challenging task that they try to solve by some techniques here. Like, for example, they take the 3D as a sequence of 2D in their model. So the data actually, they actually trying uh, to work here in different domains, in different modalities, and by using a large data set they created, and use it for the fine tuning for the SAM original model, they get actually a good result in the medical field. So the data set here was consisting like 10 different data sets. There is unbalancing here in the samples for each one, but in general, the MRI and CT and the endoscopy actually have maybe more attention in that field, more than the other maybe modalities, but they use that this amount in that unbalancing way, and they train the model on that 10 actually that 10 actually medical image mask pairs, and it was like more than 1,500,000 image mask pairs in this case, addressing maybe there more than 30 cancer type. This is like showing the performance in that CT scan, and how they can actually, based on the prompt come from the end user, can be select like multiple region, multiple area of interest, and segment them in an efficient way, just by using this fine tuning approach. The architecture of the
Mohammed, what was
yes,
going on in that, what was going on in that previous slide where there's some user involvement? It looks like they're kind of drawing a bounding box and segments only in that region or something like that.
these slides.
Yeah.
Can you raise your voice, William, a little bit?
I just was curious if you kind of like, or have we implemented something like this, or is this just in the paper? Or is it somewhere we're going?
They have actually, they implement that. They have a public repo showing exactly the same results in GitHub. So the code is available, and this is actually the results they get for this. I believe this is the liver part, and they have like 3 different approach. I just look in that yesterday late, so I didn't want through all the code, but I see you can make that even in the text mode. You can like saying for the model, give me this part specifically. So they trained the model on that text caption, so you can give, and also you can make it with the bounding box like we can see here in the example. So different, I think 3 different GitHub or Colab is available to show all the results we see here. One for the text, one for the bounding books, and I guess there is one also for the points. when you select only when you click only a point on a certain part, and it gets like the object in that area. So yeah, so here actually this is the almost the same architecture and the same one. Only the input output here is medical images, and there is actually not a lot of changes happen except this fine tuning part we talk about. And uh, the process itself starts by an image processing where we have that input size 1024 by 1024 by 3, and the result from the image embedding, it will be batching that in 16 by 16 and get like a feature size 64 by 64 after the encoding. As we said, the actually using the base vision transformer here for the lightweight it has, trying for balancing between the performance and the computational efficiency in this case. So they internally with that base vision transformer, they have the masked autoencoder uh, uh, used like in the beginning to do the initial pre-training and get the feature out from the imaging encoding part. And they train that part. They say they train that part supervised on the same the same data set again. Um, so this is for the imaging part. For the prompt encoding here, they transform the bounding box in also 256 dimensional vector embedding, and they take like in the case of the bounding box, they take the top left and the bottom right corners as an input for the positioning encoding, and make that merging or fusing between the imaging and this prompt internally in the mask decoder. So the mask decoder here have that also transformer layers, fuse this image and prompt embedding. They may be doing that using the cross attention layer. There is also a transpose convolution layer that upscale again the output of the mask decoder to get retrieve the original image size or the original image input size, and the activation at the final stage here to get the masking or the pre-mask or the object mask. So the 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 data itself, they use that 1 million, around 500,000 medical image mask pairs, and they split that in 80% for the training, 10 for the tuning, and 10 for the validation or the testing. And for the fine tuning part, they actually didn't change all the parameters. They didn't update all the parameters. They just go to the image encoder and the mask decoder parts. So in the image decoder, there was like more than 89 million parameter there, and for the mask decoder, there was like 4 million parameter. This is the part that they try to fine tune to get the results. And for the loss function here during the training process on that data, they actually use the double approach here, the dice loss and the cross entropy or C loss, summing between both of them and doing the optimization part. So the result that they get from all of that actually they outperform some task-specific model like units, for example, and deep lab version 3. Of course, they also outperform the SAM, the original one, because this one was not trained on the medical images. So Here it looks like the accuracy maybe for the task specific and mid-SAM can be a little bit close, but the advantage of mid-SAM that there is no task specific here. It can be any modalities in from that 10 different data sets or 10 different modalities in the medical images. It show a better actually performance in the DICE similarity coefficient compared also to this part. And we can see here some visualization and the images showing the performance, how it actually get better results in the segmentation part. This is so they have two sets that make the evaluation on it: internal validation set and external validation set. So in the internal validation set, this is like the testing partition of the training process, which we saw the results. For the external validation set, this is unseen data during the training that they tried to use actually here to validate, like this is the zero shot actually evaluation of that model. And here also we see the performance is doing very well. Maybe it show the best performance among all these specific task model like the unit and the original also someone. One of the tests that they performed also training that is a size effect, and yeah, it show the more data set we have there, the better for the performance internally or externally for both cases. And for the part that they use actually that model in order to help the annotator, the manual annotator save more time during the labeling, and the result showing that they reduced by 82% the time needed, or the average amount time needed for the annotation for the annotators here. So as a conclusion here, we can see that mid-SAM have that superior generalization capability across diverse medical imaging tasks, as the results show. It is still actually can be adaptable for both common and complex segmentation challenges, and I believe they believe that there is also still a margin for more actually improvement, adding more tasks in the future and adding also more data set, large more data set size to get better actually generalization for this model as a foundation model. So this is all the things that we have till now, and if we have any question.
Yeah, I have a lot of questions, but I don't know if they talk about them in the model or in the paper. Do you know how large is their models? Because what I'm confused with is the original SIM architecture has image embedder, which I assume to be a huge transformer, but I don't know how large it is. It's not in the paper. Yeah, can you scroll back? Because they're using the same architecture, right? Yeah, there is image encoder. Thank you for the slide. And then there is mask decoder, which you said it's a transformer with upsampling convolution somewhere. But image encoder, so how, because the model benefits from 1 million samples, how, do you know how large it is? How many parameters there? 10 million, 7 million, I don't know, like just thinking about the large language models and the billions of parameters. I wonder how large is this one?
They actually said something here maybe related when they make the fine tuning. So they said that for the total parameter, the image encoder, they updated like 89 million parameter. I'm not sure if this is the the basic vision encoder transformer, or this is the large one, but it's supposed that they are using the basic one, the most light one here in this case. For the mask decoder, it's around 4 million. So
Yeah,
this
this
all,
line is useful. Yeah,
Yeah.
exactly. This line is useful.
Were they doing the segmentations in 3 dimensions, or were they doing it in 2 dimensions, slices at a time? But that would save a
They,
lot.
yeah. So I see in one of the collab yesterday, they actually have an FT input, but how they treat that?
What do they have? What do they? Sorry, can you repeat? Nifty inputs in iPads. I mean, nifty inputs, but it's slices anyways, right?
Yeah, yeah. And if we go here actually for the survey paper, yeah, this one. Yeah, some models come later, like SAM Mid 3D or segmentation volume 1. I guess this is actually dealing directly with the volumetric data here, and they change it. I just look fast in that. They change it in the architecture, the internal architecture of all these parts. So they add, instead of any 2-dimensional thing, they add 3-dimensional thing, like 3D convolution, whatever. Yeah.
I think you could probably do the bounding box thing without conditioning the neural network on it, by just like doing segmentation and getting the largest connected component bounding box.
Yeah, bounding box is easy when you have the parameters.
Yeah.
If you know what. Yeah, but 3D would be much more interesting. I wonder how it works.
Maybe the next time we look in the SAM 3D and segmentation volume paper to see what is the performance. And I guess I guess one of them was actually outperform the in unit here. But I didn't go in the details, but this is maybe next time we can try to see in more details what's happening here.
Yeah, that's very interesting. Thanks for choosing this paper. Because I'm thinking interacting, say if a user gives a prompt, scribbles or points in a slice, but the model segments in 3D, that would be ideal. So I wonder, yeah, well, scribble prompt, yeah, we didn't know that one. Where does this figure come from? From the paper that you're looking at, or no?
Yeah, this is computers in biology and medicine in the up. Yeah.
Yeah, this one is very good and so recent, so quick. They already have past December, right? 2024, because Scribble prompt is 2024.
Yeah, this one actually. Let me get.
Yeah. So thanks, Mohammed. I will stop the recording now, and thank you, online listeners and viewers.